Hello, this is Chick Abbott. In this video, we're going to be talking about the solutions to sample data state space equations. Watching this video assumes that you've seen the video on solutions of continuous time state space equations and the solutions of discrete state space equations. And a sample data system is somehow a hybrid of these two concepts, and they're very common in real practical engineering applications, so it's important to see this. So what is a sample data system? A sample data system is a continuous time system in which there are major portions of your system that are run as a discrete system. So this essentially means run by a computer. A computer is a fundamentally discrete thing. It runs through its lines of code, and when it gets to the bottom of its code, it goes back up to the top and it runs through its lines of code again. And each time it does that, it updates its equations, but it doesn't know anything about what was happening in between. And so that takes a finite amount of time to do that. And while your computer is crunching numbers, the continuous world is evolving inside of it. And so you have to make these two systems match up with each other. So we're going to have some digital computer that is calculating fundamentally we should say we have some system that is a continuous time system. So x dot of t equals ax plus of t plus b u of t. But this is a continuous time system. But this u of t, let's imagine that that's some sort of voltage going to a motor. So this is your input, and you're trying to control some system, and it's a real voltage that lives in time. I mean, you can plot that voltage as a function of time, this u, and it's something that evolves. But if we're going to command that voltage out of a computer, it's not really possible for us to command a signal that's like this because the computer doesn't update itself instantaneously. So really the u coming out of a computer, it's still going to be a real, let's say, voltage or something coming out in time, but it comes out and it's held for a little while until the computer updates, and then it updates to a new value and holds to that, and then it updates to a new value and holds to that. And so all smooth signals are approximated by some discrete process. And your computer has some fixed sampling time. Let's call that period t. That's how much time it takes to run through your lines of code, to read into the signals from the A to D card, to run through the lines of code, and to output signals via the D to A. So there's going to be some fixed sampling time, and so really we don't actually have the ability to command u of t continuously in time, but instead what we're going to command is some u at sample k. And then, but of course, there really truly is a voltage that looks like this coming out of the computer, and so we have to see how does the u of t relate to the u of k that's coming out of our lines of code. And so what we have is we have that u of t is going to be equal to the u of k that we calculate, and this is going to be true for t greater than or equal to kt and less than k plus 1t. So basically that means as soon as you get to a new sample, it's going to update, u of t is going to update to that u of k value right at that instant, but then it's going to be held constant. So u of t, if this value right there is u of k, this is u of t, and that u of t is exactly equal to the u of k for this period of time, which is everything between one integer multiple of t up to the next integer multiple of t. And at that point where this equal sign would come in, you update it to the next value and you hold that constant. So u of t truly is a continuous thing, but it's just a sampled u of k held. And so what we're going to do is we want to compute a solution of x of t, because this is the system we're interested in controlling. It's truly a continuous time system, but with some understanding that we're going to only be able to control it using a method like this. So we're going to find this x of t at t equals some k times t, so some integer multiple. So basically we're going to compute x at this time, at this time, at this time, at this time. And so that's what we want to do. And if we go back to our solution for a continuous time state space equation, what we get looks like this. So, and you can go back to the solution for continuous times equations if you need to refresh, but it looks like this. I'm just plugging in kt in for everywhere that the t variable is. So it looks like e to the a kt times x naught. And then I have this integral which is now from 0 to kt e to the a kt minus tau times the b matrix times u evaluated at tau d tau. So this is just the solution of a continuous time equation, and at each place that there was a t, here, here, and here, and here, I plugged in kt. We can do the exact same thing for x at k plus 1t. So ultimately, we're talking about transitioning from some arbitrary kt to some other arbitrary k plus 1t at the next time instant. We're seeing how this evolves like this. So now this looks like a at the k plus 1t times x naught plus this integral from 0 to k plus 1t times e a to the k plus 1t, minus tau e u at tau d tau. So I have these two equations here, and they are just fact. They are just a restatement of the original equation. Then I start repackaging stuff, and I'm going to say, so this is equal to this, and it's also equal to, after I kind of repackage, e to the a t times e to the a kt x naught plus this integral from 0 to kt of e to the a kt minus tau b u at tau d tau bracket. So I've factored that e to the at out. And then the next thing here, and why do I want to do that? When I factor that out, look at what I have in between these brackets here. It's this. It's this top equation. This stuff in the brackets is x at sample kt. And so when I do that, that's just one term I haven't finished because I've broken this up here. So I need to keep continuing this factoring. So now I have this other term plus an integral from kt to k plus 1t of e to the a kt plus t minus tau times b u evaluated at tau d tau. So this is completely breaking this up into its various chunks. And so so if you look at this integral, this was going from 0 to k plus 1t. So we've broken that integral up just from 0 up until the prior step, 0 to kt, and then from kt on. Then, in this case, so from this integral, from 0 to kt, u was whatever crazy input u was. It was something that was evolving, and who knows how many steps have lived in this time. But in this one last little step, u is completely well known to us. So in this one last little step here, u of tau is equal to u of kt, because u is held constant over this one last little step, unlike the random stuff that was happening up here. So in this one little case. So the next thing we do is we let's just make our math easier, let's let this variable alpha equal kt plus t minus tau to get rid of this kind of complicated thing here. And when you do that, what you get is a highly simplified equation. It looks like x evaluated at k plus 1t in time is equal to e to the a capital T x at kt plus the integral from 0 to t e to the a alpha d alpha. And that whole thing is times by b u evaluated at kt. So everything was done here with a continuous time equation, x of t, and we were analyzing little t at some integer multiples of k capital T. But now let's lose our explicit reference to this idea of time, and let's just think of this as a discrete system. And don't even call it a discrete time system, just purely a discrete system that evolves from one sample to the next. So let's lose our explicit reference to time, and let's just call this x at sample k plus 1 is equal to e to the at times x at sample k plus this thing here, the integral from 0 to t e to the a alpha, the alpha times b times u at k. Oh, sorry, I didn't need to do that. So when I do that, what I see here is I'm almost in this formula that x to k at k plus 1 is equal to something times x of k plus something times u of k. So I can actually call this, let's call this AD, it's an n by n matrix, and let's call this whole thing here BD. And so I'm back to this form, x at sample k plus 1 is equal to some A matrix times x at k plus some B matrix times u at k. So I've taken what was a continuous time thing, I've acknowledged that it's being controlled by some sort of computer that can only update the input to the physical system in these discrete steps and hold them during the computation time. And I've turned this into this discrete system that truly is a discrete system. And if I want to look at the solution of how this equation x at k evolves, and I can say evolves over time, but again, we don't have to think of it in time, I can say how it evolves. X at one sample, x at the next sample, x at the next sample. I do this analysis now using the techniques described in the solutions of discrete state space equations video, not the solutions of continuous state space equations. And so we've made this effectively into a discrete system. Now, if you look at it, I mean, our A matrix fundamentally has our sampling period t embedded in it. So if we take, this matrix A essentially represents our real physical system, it's a continuous time thing. Our capital T here represents our sampling period of our computer, and this A to D somehow capitalizes on both of those things. It's our continuous system if we only look at it every capital T seconds. We get something that looks like this. And so this is a nice result, and it works really well if the assumption that u of k is constant between samples is accurate. Now, all of the samples that are coming out of our computer, that's going to be completely accurate for. But what happens when some of your inputs aren't coming out of the computer? So maybe you've got some system that you're trying to control, and one of its inputs is a voltage from a computer. Perfect model. What if the second input, though, is wind that's blowing? Now, the wind isn't coming in these discrete. Wind doesn't evolve like this in time. Wind really truly is a continuous thing. So basically the question you have to ask yourself is, over the time period that my computer runs, is it reasonable to model all of my inputs as being almost constant during that period? So the real question you have to ask is, are my other inputs significantly evolving within the sampling period? A common sampling period for a sample data system with a computer is 1,000 hertz. So your time step t is equal to 0.001 thousandth of a second. So the question you have to ask yourself is the wind changing a lot within a thousandth of a second? And then you say, no, it's not really. It takes maybe multiple seconds to really change. And so over the course of a thousandth of a second, you can model it very accurately as being constant. Then this kind of sample data model is still going to be very accurate for you. But in the case of something like a high voltage noise or something that's changing significantly between samples, then that's probably not going to be a very model. But this is going to work a lot in real life.